Hey there, and welcome to my video on doing integration with U substitution. Integration with calculus can get relatively complicated at times, and it almost seems like, is there an actual reason for it? Like there's a reason we needed to integrate this thing, or are you just trying to make things as complicated as they can be? To which I don't know the answer, but we do have a method for which we can try and at least sort through it. And that's U substitution. It can take a relatively complicated problem and make it more simplified to allow us to integrate things a little bit easier. And what it tells you here at the beginning, where it's talking about U substitution, is the key to U substitution. This very first statement, the key to U substitution is to try and find something in the integrand where the derivative of that is already present. And that will try to simplify things for us when we are working out the problem. So looking at the procedures here, the first part's basically already been stated. Look for a piece of the function whose derivative is also in the function. And if you're not sure what to use, try looking for something that can have a fraction for a denominator or something raised to a power in the function. And what we're going to do is we're going to take whatever that thing that we've identified as, and we're going to set u equal to it. And when whatever that expression is, we take the derivative of that expression. And then third here it says use your u and du expressions to replace the parts of the original integrand. And then you should be able to work out the remainder of the problem relatively simply. And I say relatively because there are going to be times when things get a little bit more complicated than others. Here the rule of substitution in the integration is comparable to the chain rule in differentiation, and here they're giving you a very kind of mathy explanation for what U substitution is going to do. So like I said, usually when we do U substitution, it's not going to be something that we can integrate directly very easily. So it's not going to be something like that's just a polynomial. Maybe it's a polynomial multiplied by something to an x power, or maybe it's a logarithm that is also being multiplied by some other function or some other expression. So what we do is we try to find something that we can differentiate and will also be located in the integrand. And essentially here what they're showing us is the mathy way of doing it. Now usually, even when I look at this stuff, I'm like, it doesn't really, I mean I can follow it, but if you actually work out some problems using U substitution and you go back and you try and read this part again, it'll probably make a little bit more sense. So essentially what we're trying to do is we're trying to establish something that we're going to associate as U. So here we're kind of looking at, like, this is U. And then we're going to take the derivative of U, which is where they're getting this. This is U prime, or du in this case. And du, and I really should kind of look at it like this, the whole thing, this is going to be du. And so we wind up with, usually at this point, something simpler to do than what we started with. And then we integrate it. We take the antiderivative of whatever we have, and if we're doing indefinite integration, we need to make sure we incorporate the constant value of c. And then after you've done the integration, you take whatever your value of u was, and you're going to just go back here and substitute it. And that's all we're doing. So hopefully the concept is something that will be straightforward enough that once we start doing this, again, if you need to come back and look at it, maybe it'll make a little bit more sense to you. But let's go ahead and jump into some expressions here. Now this first part, the first couple of examples, I'm going to probably go into a little bit more detail than I necessarily would if I was just working out, say, an answer key or just trying to perform an integration on my own for whatever reason, just so that way we can kind of see what's going on. Because the first examples that we're looking at here, part A and B, they're nice introductory examples for what we're looking at. So ideally what we want to try and do is we want to see, is there something in the integrand itself that if I take its derivative is already present? And that in this case would be the expression x squared plus 1. If I take the derivative of the x squared plus 1, not to the second power, just the expression inside of the parentheses, I'm going to wind up with that 2x right there. Okay? So what that is allowing me to recognize is that this right here is going to be my u value that I'm going to do my substitution with. So here, what we're going to say is I'll say u will simply be x squared plus 1. Now, this is where I say I'm going to go maybe in a little bit extra steps here so that we take the derivative here. And here I'm not going to do u prime on these because I want to make sure that I don't lose anything in the explanation here. So we're taking the derivative of u with respect to x, so du dx. And we actually take the derivative of the right side, which is where we get the 2x from. Now, if we go back, let's just jump back real quick. One more page. If we jump back real quick, what we're trying to get is something. We're trying to get something that looks like this. Okay? The function with respect to u du. So going back here to the example, let me go back to my blue color here. We want to try to get u by itself. I'm sorry, not u, but du. So I'm going to take the dx that's in the denominator, I'm going to multiply it to both sides, and I'm going to say du is going to be equal to 2x dx. And if you notice, this and this are the same thing now. So that will allow me to take, let me try not to get my colors too convoluted here. We can take this expression and substitute u with it, and I can take the 2x dx and I can substitute du with it. And what we're going to end up with when I do that u substitution is my integration now is going to simply be the indefinite integral of u squared du. Because we're replacing the expression inside of the parentheses with u, but of course it's squared, which is why we get the u squared. And everything that's left over, the 2x dx, has been expressed as du. Now, at this point, we can find our antiderivative. So here, at this point, this is where we find the antiderivative. So the antiderivative of u squared, at this point we treat it just like it's a polynomial, u to the second power. So this is going to give me, and we don't really have anything in particular as far as a value, a variable or an expression that we have. So I'm going to just call it big F prime or big F of x. So the antiderivative here in this case is going to be 1/3 u to the third power plus a constant of integration. And now that I've actually, and so now I've done the integration. Now we can take the expression that we had for u and substitute it back into the problem. So I don't need to change my colors here. So we're going to take the expression that we had for u and substitute it back into the expression. And so my final, oops, capital F, my final antiderivative in this case will be 1/3 times x squared plus 1 quantity cubed plus the constant of integration. And there is how we're using U substitution to take something that would have been a little bit tricky. What I probably would have done was, if I didn't use U substitution for this one, I probably would have just tried to multiply through everything and put it in standard form, and then tried to take the integration of it. But using U substitution, it's going to save us a little bit of work. So let's move on. Let's try another example here. Let's try this green color. So what we're looking at here is we want to see, okay, can we identify something in the problem again that if I take its derivative will be present somewhere else in the integrand. Now, sometimes it's helpful to make sure that you have whatever your trig operation is. Sometimes it's useful to make sure that it's in parentheses. So in this case, what we're going to have, I'm going to look at the 4x as u. That's what I'm going to be looking at as u. So here, u will be equal to 4x. So if I take the derivative of both sides, du dx, the derivative of u with respect to x, I'm going to get a 4. And again, multiplying both sides by dx, so I can just say du is equal to something. We're going to say du is equal to 4 dx. Now, where is that in the problem? That 4 dx is right here, 4 dx. And that's what we're trying to work with in this case. So now we can set up our integration with our U substitution here. Let me pick another color so everything doesn't all blend together. Let's try that color there, orangish or whatever that is. So using my U substitution, here I'm going to have an indefinite integral of, now again, we're not doing anything with the cosine. The cosine is still there. So this one will be cosine of u du, because the two things that I underlined in yellow represent what was left over after I took the derivative of the 4x, in this case 4 dx. And now I can take the antiderivative. So here again I'll just say big F of x, just to have something. So the antiderivative of cosine will be sine. So I'm going to say sine of u plus my constant of integration. And it really should be kind of a capital C. Ugh. Why no right C? No good. C. There we go. That looks better. And now that I have that integration done, now it's just time to go back and substitute the expression that I set for u. So now I'm going to take this 4x that's here, and it's going to just drop right back in here. So I get sine of 4x, with or without the parentheses, plus the constant of integration, c. So hopefully these two examples are getting you a good idea of what we're going to be looking at with U substitution. Now, of course, these were good, relatively simple examples to use with U substitution just to get your feet wet. Some of the examples that we're going to see in this presentation are going to get a little bit more complicated. And I'll go ahead and do the first couple here, C and D, because things are going to start to get slightly more complicated. Actually, looking ahead, I think I will try to do C and E, and then I'll ask you guys to do D and F on this page and see how you do. Okay, so let's take a look at example C. What we're looking for is to see, okay, is there something in the problem that if I take its derivative, I will find it somewhere else in the problem. And that is this guy right here. If I take the derivative of the 4x squared plus 1, I'm going to be left with the 8x. So here we'll say the u value, in this case, will be 4 x squared plus 1. Now at this point I'm not going to write it as du dx because understanding that after we've seen it in the last two examples, we're always going to wind up multiplying whatever we take the derivative of by dx. So in this case, we're going to just jump right to the derivative here to being 8x dx, which of course we can see here is the remainder. So 8x dx, that is going to be du. Oh, and du. Okay. So I guess we'll put the right color, du. So now what we have is we can take our indefinite integral, and I guess I'll go to another color here. We have our indefinite integral of, in this case, the square root of u du. Now we take the antiderivative here. So if you want to, you can go ahead and turn the square root of u into a radical. And so you can say u to the 1/2 power du, if that makes it a little easier to see how we're going to do the antiderivative. And when I do the antiderivative in this case, I will say this will give me 2/3 u to the 3/2 power plus the constant of integration. And now that I've done the integration of the expression doing with U substitution, now we can take the expression that we have for U and plug it back into here. And I would say f of x is equal to 2/3 times 4x squared plus 1 raised to the 3/2 power. And if you want to, you could write that as a, the square root of 4x plus, or 4x squared plus 1 cubed, whichever way you prefer, plus c. And there we go. There's your integration. So I'm going to skip D and have you guys work that one independently. I wanted to go ahead and jump down here to E, because here you're going to see something when we do our U substitution that you haven't quite seen yet. Okay, so the very first thing that I want to do for this one is I don't like it written as the fraction that was given to me. So I'm going to rewrite this as the indefinite integral of x times 4x squared plus 3 to the negative 6th power dx. Okay. Now when you're looking at this one here, you're going to say, okay, well, what's u going to be? Well, in this case, u is going to be this expression inside of the parentheses. Now, I know you're probably saying, okay, well, Mr. Piercy, if this is u, if I take the derivative of that, I don't get something else that's left inside of the integrand there. I don't get the x times dx. And that's part of the reason why I wanted to work this problem out for you. So here we're going to say u will be the 4x squared plus 3, and when I take the derivative of that, I'm going to get 8x dx. Now the difference in what we have, again, just kind of looking at what we have left over here and left over here, x dx, you can see currently they don't match. Okay, so I need to do something to make them match. And what I'm going to do at this point is I'm going to multiply by 1/8, so that way I will have 1x dx when I'm done. And so what I'm doing, again, multiplying both sides by 1/8, I'm going to get 1/8 du to be equal to x dx. So the x dx that's remaining in the integral that right now, we can replace it with 1/8 du. So let's transition to a new color here, just so we can see what's happening. So I'm going to say the indefinite integral, in this case, what we're going to have will be like 1/8 u to the negative 6th power du. And the 1/8 can be pulled out using properties of integrals. We can pull out the constant 1/8 integral u to the negative 6th du. You could have just jumped to that one if you wanted to, but not everybody is going to see the constant to be pulled out straight away, so that's why I didn't want to skip anything. And now we'll take the antiderivative of the expression that we have. So we have 1/8, and in this case, if I take the antiderivative of u to the negative 6th power, I'm going to wind up with negative 1/5 u to the negative 5th, and plus a constant of integration. Constant. Why can't I write a C today? Now we don't want to do the distribution with the 1/8 at any point until we're kind of almost done. Now we want to go ahead and take this u expression that we had, and we want to go ahead and plug it back in here. We want to go back and substitute it now. So this will give me 1/8 times negative 1/5, and in parentheses here I'll have the 4x squared plus 3 to the negative 5th power plus the constant of integration. And now we can put in the do the distribution here, and I can say in this case it's really going to look like it's going to be a negative number overall, because we have a positive 1/8 times negative 1/5. So really we're going to have just a 1 in the numerator over a 40 in the denominator times 4x squared plus 3 raised to the 5th power plus your constant of integration. So that's why I wanted to work that one out, because when we did our U substitution here on the, or when we were looking at our U values here on the left, we didn't get something that was exactly going to match the rest of the integrand if I took the derivative of something. So that happens sometimes, but you can manipulate it algebraically to make it match. In this case, by multiplying both sides of du to be by 1/8, and that's how we got the 1/8 du to represent the x dx that was left over in the original integrand. So here at this point, guys, let me go ahead and slide it back up so if anybody needs to see it, they can see it. Go ahead and try working out examples D and F on your own. And when you're done, hit play and see how your work looks compared to mine. All right, ladies and gentlemen, how did you do? The example D on the right side worked out to be 1/8 times x squared plus 2 quantity to the 4th power plus your constant of integration. And moving on to F, it's kind of the same thing. The first thing I did on F, however, is I rewrote the integrand from being in radical form to being in exponential form, and wound up with a negative 1/14 times 7 minus 2x cubed, raised, all of it raised to the 7/3 power, plus the constant of integration c. So hopefully things are moving along okay as far as your understanding. If not, make sure you're writing any questions that you may have down, so that way you know to ask them later on. So here we have a couple more examples, and again I will do a couple of them for you and ask you to try and see, can you do a couple of them yourselves. So I'm going to go ahead and do the two on the top, G and H, because here we're getting into kind of the transcendental type functions where we're having something raised to a power like e or natural log or trig stuff, and and so on. So looking at the function that we have here in G, I'm going to look at U as being the radicand of sine x plus 2. So when I take the derivative of that, I'm going to get du is equal to cosine of x dx. So we have our matching stuff, cosine of x dx. And if you want to, you can rewrite the expression as a radical, and that's what I'm going to do as I convert it into an integral here. So I'm going to say the integral of u to the 1/2 power instead of the square root, because my mind just operates with that easier to do the antiderivative du. So here the antiderivative of u to the 1/2 power will be 2/3 u to the 3/2 power plus the constant of integration. And now we can take the u value and substitute it back into the expression that I have here in red, and we're going to be left with, in this case, f of x, or the antiderivative will be equal to 2/3 times sine of x plus 2, all of that raised to the 3/2 power plus a constant of integration. And there is the antiderivative for G. And moving on, let's try to take a look at H and see how we do on H. Let's get another color here. So the U value that I'm going to look at in this example is really just this bit here, because if I look at the 4t cubed, if I take the derivative of that, you can see that we will get the 12t squared. So in this case, I'm going to say u is going to be equal to 4t. So du, 4t cubed. So du in this case will be 12t squared dt in this case, because that's the variable that we're doing the derivative with respect to, is t instead of x this time. And now that I have that, we can rewrite the integral with our U substitution. And so let's do that. So I'm going to say the indefinite integral of e to the u power du. Because now that's the whole point of doing the U substitution, is try and simplify the integrand so it's easier to handle. So now we can take the antiderivative, and in this case the antiderivative of e to the u is just e to the u plus a constant of integration. So finishing off the problem by substituting the 4t cubed back in for u, I wind up with e to the 4t cubed power plus my constant of integration. So moving on to these two examples here, again, this is where I'm going to strongly encourage you to go ahead and pause the video, try working out these two and see how you do. And when you're done, hit play and check your work and see how it looks against mine. Okay, so here are the last two that I asked you to do. Checking your work, make sure that starting off with the correct U component is going to be pretty important here. So on the first one, natural log of x is what I'm doing for u. The derivative or the antiderivative of natural log of x will be 1/x, and substituting that into u du gives me 1/2 times the natural log of x squared plus c. Now on that one, we're not going to try and use any kind of properties of logarithms, because we're squaring the quantity of x or natural log of x, and not the component of x itself. And the last one, J, this one might have been a little bit confusing, but you can recognize that sine and cosine could have been either one, really, of U, but because cosine is having an exponent of 4, that makes it the better candidate to be U in this case. So the derivative of cosine gives me negative sine of x dx. And so if you notice what's left over in the problem that was given to me was a positive sine of x dx. So you have to multiply by -1. So we get negative du to be sine of x dx. So that's what we substitute into the problem. But of course, the negative can be pulled out as a constant. So that's why I'm doing the integral as negative integration of u to the 4th power dx. So take the antiderivative, u to the 4th, and then substitute cosine back in for u. So we got a couple more examples to keep working with here, just to make sure that you're doing them. And in this case, I'm going to just go ahead and pause the video and work these out, so that way, you know, the length of the video doesn't get excessively long. So while go ahead and try working these out as well on your own, because at this point there's really not much new material in the way that we're presenting this stuff. It's just, can you identify a component of U, so that way you can simply integrate an expression and then go back and resubstitute your value of U and have your final expression. So I'm going to go ahead and pause the video. You do the same. Try to work these out and check your answers with mine, okay? Okay, and so here are the next two worked out. Hopefully you're able to pause the video and work these out okay on your own. The first one, K, on the left, what I'm doing first at the beginning is the expression on the right, in the right set of parentheses, e to the x cubed times e to the x. I'm going to just use the properties of exponents to show that that would be the same thing as e to the x cubed plus x power. And that expression, x cubed plus x power, you can see is the, if I take the derivative of that, I get the 3x squared plus 1 that's in the left side parentheses. So that's why I'm calling that u. And we wind up with the final integration of e to the x cubed plus x powered plus the constant of integration. The example on the right, I decided I wanted to break it up into two separate fractions, so that way it was a little bit easier to see what I was going to be looking at. But again, the e to the 3t power in the denominator, or 3 plus e to the 3t power in the denominator, if I take the derivative of that, I wind up with e to the 3t power left over. So that's why I'm calling 3 plus e to the 3t power my u value. Chain rule produces 3e to the 3t power, which of course does not match what would be left over in the integrand. So I divide both sides by 1/3, or multiply both sides by 1/3, I should say. And that's why I get the constant of 1/3 for my integral when I'm doing my integration on the right. So moving on to the next couple of examples. Again, go ahead and pause the video and work the problems out. And when you're done, hit play, and the answers will magically appear on the screen so you can check your work and see how they compare with mine. All right, and here are the last two indefinite integration examples that we're looking at with U substitution. M kind of threw me for a loop when I was taking a look at it originally, because we can use properties of integrals to break up the expression, because the integration of 1 over x by itself isn't difficult to do. There's nothing crazy to do with it. But the 3 to the x power, if we can isolate that into its own integral, then we can use U substitution easily with just that piece. So that's what I'm doing, is I'm breaking up the 3 to the x power and the 1 over x into separate integrals. Now, what I'm looking at is I'm looking at 3 to the x power as being what I'm looking at for u. So when I take the differentiate that, I get 3x times the natural log of 3 dx, which of course does not match what is inside of the integral. In fact, inside of the integral, all we have is just 3x dx, or 3 to the x power dx. And I just realized that I didn't write my expressions correctly here. So let me clean that up real quick. This should be, I wrote it as 3x as opposed to 3 to the x power for some reason. So 3 to the x power here and to the x power here. And there we go. Now so when I take the, at this point here, after we take the derivative of u, we get 3 to the x power times natural log of 3 dx. And clearly, that expression, that integral, does not have anything with the natural log of 3, so we multiply it by its reciprocal to get 1 over natural log of 3 du to be equal to 3 to the x dx. So in this case, after I've done the third line in the blue on the left side of the screen, obviously the 1 over natural log of 3 is a constant. We can keep that outside of the integral sign. But in this case, when we try to simplify the integrand, we don't have a u. We just have the expression for du, the 3 to the x dx. So that's what I substitute with, is just 3 to the x dx. We don't have a u value that we're actually substituting back into either of the integrands. And then we go from there. So substituting the 3 to the x dx for du, and then we take the antiderivative of both of those. So I'll get 1 over natural log of 3 times 3 to the x power plus the natural log of x as an absolute value plus c. And for the last one on here, and I don't know what I did, apparently I guess maybe I erased something. I don't know what happened to my u x, oops, x squared. There you go. So I'm saying u is going to be the expression sine of x squared plus 5. So the derivative of that will be 2x cosine x squared dx using the chain rule. And my 1/2 got cut off over here too. I don't know how I erased this. 1 over 2. So we divide both sides, or multiply both sides by 1/2, and so that's how I'm getting 1/2 du to be equivalent to the x cosine squared dx that's left over inside of the original integrand. So we're rewriting the problem with our u substitution. We have the constant of 1/2 that we leave outside of the integral, and in this case we're just going to have u du. And so we substitute. In this case, the antiderivative of u will be 1/2 u squared. And I forgot to square something here. There it is. Now I see it. I forgot to square right there. Because we're squaring u. And so this should be squared at that point there. And actually I put my, that square isn't there. It's really here. It's all the little details that are getting me on these. I had to rework this problem already because I realized I made a mistake. I just forgot something at some point, and I had to rework it out. And it's always just the little details that get me. It's not that I don't know what I'm doing. It's just, man, I forgot a parenthesis or forgot to add a number. Like the first time I worked out the problem, I completely left off the +5 for some reason. I don't know why, for u. So anyway, that is going to wrap up the stuff we're looking at with indefinite integrals. Now, if you're following along with your notes, the next thing that it's giving you here is just the general power rule for integration. And honestly, I don't know why they're putting it here kind of at the end, because we've been doing the power rule for integration already. And what we're moving on to now is just some examples with some definite integrals with integration. So here, when using u substitution with a definite integral, it is convenient to determine the limits of integration for the variable u rather than to convert the antiderivative back to the variable x and evaluate at the original limits. So what this is going to do is it's going to show us a method of how we can kind of evaluate a definite integral using U substitution without having to, again, it's meant to simplify the process that you're doing and still produce the same result as if you had done it the long way around. So again, looking at the mathy definition of what we're seeing here will make a little bit more sense. So what we're seeing on the left side of the integrand here, we have our normal upper and lower bounds where we're going to evaluate the function. Well, what I'm going to do is after I've identified what my u value is, and I can then take that u value, whatever it is, and I can evaluate it with those upper and lower bounds and find out what their outputs are. And that will now become my upper and lower bounds for the integration as we use U substitution. So let's take a look and see what we're going to do with this. Now again, the first couple here, I'm going to do maybe in a little bit more detail than is strictly necessary, but I don't want to kind of leave anything off here. So in this case, again, we're just doing U substitution, and I can look and say in the integrand itself, what part can I take the derivative of that's already present in the integrand? And if I take the derivative of tangent of x, its derivative is secant squared of x. So we can look at this one here for our u value. So in this case, I'm going to say that u is going to be the tangent of x, and when I take the derivative of that, du will be equal to, nope, not tangent, don't write tangent again, will be secant squared of x dx. So now here, this is what it was looking at for just, how we're going to look at a definite integral now, okay? And here, I'm going to go ahead and write this out so it's pretty plain what we're doing. So here, this is what my thinking in my head is. When x is equal to 0, what does u equal? Okay. So we're going to say u is equal to tangent of 0. We're going to just substitute 0 for x now. And if I evaluate that on my unit circle, tangent of 0 in this case is 0. And I'm going to do the same thing for pi over 4. So let's pick a different color here for pi over 4. Let's see, something that'll stand out but is different than enough from the blue. So here we can look at it at pi over 4. So again, what is u when x is pi over 4? So here I'm going to say u is equal to tangent of pi over 4, and then you again evaluate that using the unit circle, and in this case I'm going to get a 1. So what I have now is in blue on the left, this is still my lower bound because we started off with the lower bound and we got a smaller number than we did the second time around, and this one here is my upper bound. So all we're doing is we're taking the upper and lower bounds that were given to us by the definite integral and substituting into the expression that we're seeing for u. And what those are going to be is that now this stuff here is now going to be my new lower and upper bound for the integral that I'm going to work out now using U substitution. So now we have, we don't have anything that we're pulling out here, so I have my integral symbol. My lower bound is now from 0 to 1. And in this case, we have u for tangent of x, and we have du for secant squared of x dx. So now we're going to take the antiderivative of this. So f of x, big F of x, would be equal to, in this case, 1/2 times, nope, I don't need a parenthesis, 1/2 times u squared, and we're going to evaluate it, in this case, from 0 to 1. So now we can start plugging in some numbers here into our given function. So in this case, I'm going to say 1/2 of, and again, we'll take the expression, and you can either substitute it here, and you can say tangent of 1 minus tangent of 0 for our definite integral process. And in this case, tangent of 1 is going to give me, nope, let me back that up just a little bit. Let's keep using our U substitution, because that's the whole point, is to try and keep things simplified. So here we can say U squared, which would be, here, let's look at it like this: f of b, the upper bound, minus f of a, the lower bound, where we're just going to use u. So u squared, in this case, would be 1 squared, minus u squared again, 0 squared for the upper and lower bounds. So we get 1/2 of 1, which is just 1/2. And that is what we're going to look at with U substitution for a definite integral, instead of trying to take the antiderivative of the whole thing and still using 0 to 4 pi as their lower and upper bounds. So let's move on. Let's try our last example here. Or this is the last one I'm going to work out, and then I'm going to ask you guys to try and do the last two in the notes. So again, what is u going to be first? In this case, what I'm looking at for u in this particular problem is I'm thinking of u as being the cosine of 2 theta. So when I take the derivative of that, du, well, the derivative of cosine is going to be the negative sign, but I have to use a chain rule here with the 2 theta. So this is going to be negative 2 sine of 2 theta dx. And does it match what we have in the problem already? So negative 2 sine of dx? No, it does not. All we're left with, all we have remaining in the original, oh, and I should say theta here, not 2x, d theta. So I do need to get rid of the negative 2 because I don't have it here in my original integrand. So this will be negative 1/2 du will be equal to sine of 2 theta d theta. So now we have sine of 2 theta d theta. We have it matching what was in the original integrand. Now, again, what we're going to do is we're going to ask ourselves, well, let's evaluate it for the given values that we have. So again, I'm going to ask myself, when x in this case is equal to 0, u is going to be equal to what? So here I would say, we're going to say cosine, or start off with u, because that's what we're solving for. So u would be equal to cosine of 2 times 0, which is just 0. And cosine of 0 in this case is going to be a 1. And let's do it again with, instead of, what was it, 0, now we're at pi over 6. When x is equal to pi over 6, what is u going to be? So we'll take up this side of the screen here. So u is equal to cosine pi over 6 would be just pi over 3 when I substitute it by multiplying by 2. And in this case, u will be equal to 1/2. Now, one of the things that we notice, or that I want to point out here, is that in this example for our definite integration, and let me pick a different color here, something that, different than what we have so far. My upper bound, my lower bound at 0 produced a 1, whereas my upper bound at pi over 6 produced 1/2. So the lower bound produced a larger number than the upper bound did. So this is going to require us to remember some properties about integrals. Remember, if we say the definite integral from a to b of f of x, well, if we turn those around, where the lower bound is at the bottom or at the top and the upper bound is at the bottom, we would change that to be negative integral b to a when the upper and lower bounds trade places. Okay, so that's essentially what we're seeing here. Okay, by having my lower bound of 0 give me a u value of 1, my lower bound has now become the larger number, and the pi over 6, which was the upper bound, produced a 1/2. My upper bound is now actually smaller than what I started with. So what we do need to do is we need to incorporate this rule, properties of integration, here on this particular example. And let's see what we have. So let's move on. Let's try another color here. Let's go, what haven't I used? I got so many stinking colors here. But I try to keep things different so colors mean something here. So now what I'm going to do is I have the negative 1/2, okay? I have the negative 1/2 from the constant that got pulled out, but I'm also multiplying it according to the rule that we have. We're going to multiply that by a negative, okay, by turning the upper and lower bounds back where they're supposed to be. So my lower bound will be the 1/2, and my upper bound will be the 1. And in this case, what was my original function? I can't see. Sine of 2 theta over cosine cubed of 2 theta. In this case, because we have u, we're going to have 1 over u to the cubed, 1 over u to the cubed, u to the third power, times du, which is the sine of 2 theta d theta. So on the left side, the negatives become positive. So I have the 1/2 to 1 over u cubed du. And now I can move it down and have some space to work. So now I can actually do the anti-differentiation. The antiderivative in this case, I will have a constant of 1/2 pulled out here. And if you want to, you can look at this here as u to the negative third power du, as opposed to 1 over 3, if that makes it easier to see. So when I take the antiderivative of that, I'm going to get 1/2 u to the negative 2 power, and we're not evaluating it we don't have to add a constant of integration here, so we're going to do it from 1/2 to 1. So again, we're just taking those numbers and we're going to substitute them into the function. But first thing I'm going to do is I'm going to go ahead and pull out that 1/2 there, and I'm going to just make this to be 1/4 times u to the negative 2 power evaluated from 1/2 to 1. And now I'll go ahead and do my substitution here. So I'm going to get 1/4 times the upper bound, 1 to the negative 2 power, minus the lower bound, 1/2 to the negative 2 power, and see what we end up with when we work it out. Oh. So here, 1 to the negative 2 power is really just going to work out to be 1, because you could use properties of exponents to just move it to the denominator. Ooh, and that's a 4, not a 2. So 1 to the negative 2 power is really just going to be a 1. And the 1/2 to the negative 2 power, that's like saying, 1 over 1/2 squared. So 1 over 1/2 squared is going to be 1 over 1/4, which will be a -4. And so here we're going to get -3 inside of the parentheses, so the whole thing simplifies to be -3/4. So there's 2 more examples that I'd like you to take a look at here, and I want you to go ahead and pause the video and try working out these 2 examples on your own, just to see if what we've been talking about makes sense. And when you're done, hit play and check your answers compared to mine. Alrighty, here are the last 2 examples. Hopefully you were able to get these without too much difficulty. In this case, again, you do need to check to see, once you've identified your u value, to identify your new upper and lower bounds for your definite integral when you do your u substitution. Ask yourself, when x is equal to the lower bound and upper bound, what does u actually equal? So you can get your new upper and lower bounds. Just pay attention to make sure if the numbers flip-flop on you like they did on example B. So on the example C on the left, I got 52/3, and example D on the right, I got natural log of 6 over 10, whatever that number actually works out to be. So that is going to kind of wrap it up for examples that we're looking at with U substitution for integration. Hopefully you were able to get some useful information out of this, and if you have any questions, let me know. And until next time, guys, thanks for watching, take care, and be good.